Welcome to final countdown. Week 9, day 3. Let's get back to work. Right. Question number 1. Question number 1. So here these are operational amplifier. These are operational amplifier. Output is connected to the input, so it's a feedback. It's a closed loop circuit. Figure shows an operational amplifier circuit with a light dependent resistor, LDR, and a 1 kilo ohm resistor. The supply voltage to the operational amplifier is plus or minus 16.5 volts. Saturation voltage is very important, plus or minus 15 volts. The resistance of the LDR is 1 mega ohm at complete darkness and 100 ohm at brightness. So LDR works for two resistors. When it's dark, when it's bright. Approximate values for the output voltage in complete darkness. Okay, let's talk about complete darkness first. Complete darkness, 1 mega ohm here. 1 mega ohm here. Closed loop circuit, golden rule number 1. Golden rule number 1. V plus equals V minus. V plus equals V minus. Now V plus is equal to 1.5 volts. So V minus here is equal to 1.5 volts. Golden rule number 2 means there is no current input. Current cannot travel into the inputs. Right. So here V minus 1.5. So here it's 1.5 volts. Right. Okay. So they've all the output voltage. So you can take this part separately. Here 1 kilo ohm. That's 1000 ohm. Here you have grounded 1 mega ohm. 10 to the power 6 ohm. Here voltage 1.5. Here is your output voltage. Let's see. Output voltage can never exceed the supply. Don't forget that. So here you can say 10 to the power 6 times total voltage divided by the addition 1000 plus 10 to the power 6. That is equal to 1.5. So if you consider mega and kilo, so here actually approximately you can get the answer, but if you look at it, so 10 to the power 6 and 1000, 1 million and 1000, how much? 1 million and 1000 rupees. So there itself is going to be approximately the same. So output voltage is going to be approximately 1.5 volts. Output voltage is going to be approximately 1.5 volts. That is going to be less than the supply, so it's okay. These in darkness. These in darkness. When there is light, brightness. When it's brightness, 100 ohm here. So 100 ohm there. I'll erase that. But the basic golden rule number 1 is the same. Here V minus is 1.5. So here if I look at it, $100 ohm, 1.5, 1000 ohm. Here V output. So if you simplify this, you can easily get 100 into output voltage, 1000 plus 100 is 1.5. So 1100 output voltage, 1100 multiplied by 1.5 divided by 100. 2020. So output voltage here 16.5 volts plus. So the value it will saturate at 50. So output will saturate at 50 plus 15 volts. Output will saturate at 15 plus 15 volts. So the output voltages will be 1.5 and 15 volt, which means the correct answer is answer number 1. Correct answer is answer number 1. Okay, right. Have a look. Active mode. Vc is greater than 0, less than Vcc. Right. Here base emitter is given 0.6. So here you can say Vb minus Ve 0.6. Vb is 0. So Ve is equal to minus 0.6. If that is minus 0.6, high potential, low potential, now current is going to be IE here. So you can say VE minus 10. Current is IE times 4.7 kilo ohm. Minus 0.6 plus 10. IE times 4.7 times 10 to the power 3. Simplify this, 9.4 divided by 4.7, 10 to the power minus 3 is IE. From this you can say 2 milliampere. But IE is approximately equal to IC, 2 milliamperes. Now you can work the problem out. They want VCE, I think. Yeah, VCE. Voltage here. So this branch you can apply. If you want from here to here or the total one. So plus 10 minus VE 0.6, that is equal to IC into 3.3 10 to the power 3 plus VCE. So 10.6. VC is 2 milliamperes. 3.3 10 to the power 3 VCE. 10.6 minus 6.6 VCE. VCE is equal to 4 volts. VCE equals 4 volts. Answer is answer number 3. Answer is answer number 3. Right. As shown in the figure, a device is made to measure the magnitude of a force by applying it to a uniform metal rod of length L and cross-sectional area A, measuring the resultant compression delta L. E is the Young's modulus of the metal of the rod. The smallest value of the compression can be measured with a measuring instrument attached to its delta L naught. If the smallest value of F that can be measured with the device is F naught, then the length L of the rod should be such that. So, have a look. Force equals A Young's modulus. Young's modulus, they are using the symbol E, over initial length times compression or extension. These are basic equations. So you are measuring the resultant compression. So you are pushing it from here. They are telling you the smallest value of the compression that can be measured is delta L. Smallest value of F that can be measured with the device is F naught. So smallest force will give you smaller compression. So X is equal to F naught L divided by AE. Here, F naught L divided by AE. Smaller force, smaller compression. So the smallest compression that can be measured, smallest value of the compression that can be measured is what? Right. So here, if you look at it, so X is found now. For F naught, X is found. Okay. For F naught, X is found. So the smallest value means X should be greater or equal to delta L naught. That's the whole idea. X can't be smaller than L naught, greater or equal. So here, F naught L over AE greater or equal to delta L naught. So L here is equal to AE over F naught times delta L naught. So this is given by answer number 1. This is given by answer number 1. Right. As shown in the figure, a child sitting on a rotating chair rotates with angular velocity omega. The moment of inertia of the system around the child is 2 kilogram 2 kg m square, as shown in the figure. While rotating, the child catches a ring 4 kg, diameter 1. So diameter 1 means radius is 0.5. From here, moment of inertia of the ring is mass equals 4 kilogram, 4 times 0.5 square. So 0.25 times 4, 1 kg m square, 0.25 times 4. Right. So final angular momentum of the whole system will be, so initial angular momentum, I think angular velocity actually, I1 omega 1 equals I2 omega 2. Initial moment of inertia 2. Angular velocity omega. Finally, child is also rotating, ring is also rotating, omega 2. Omega 2 is equal to omega divided by 3. 2 omega divided by 3. Answer is answer number 2. Answer is answer number 2. But here I think they made a mistake by putting angular momentum. But I think actually they want is angular velocity. So maybe that way they gave it as all. I don't know, but they are asking angular momentum. But they are given answers to angular velocity. Right. Next one. A boat made of metal floats in water with 1/5 of the volume submerged. So 1/5 of the volume is submerged. So here upthrust balances the weight. V over 5, density of water into G is mg. Question number 1. If a second boat is made with a volume 5 times bigger than the first, using the same mass, then the ratio of the maximum load that can be carried by the second boat to the maximum load that can be carried by the first boat. Maximum load means just about to submerge. So here, apart from the weight, maximum load M dash. So here we can write V rho WG mg plus m dash g minus 2 minus 1. 2 minus 1 is 4 over 5v rho w m dash g. Now they are saying five times the volume, same mass. 5 times the volume means 5. Same mass means what's your submerged volume? Submerged volume should be same. Very simple. Submerged volume should be same. VO of 5. Now maximum load. mg plus m double dash g. Everybody is submerged. 5v rho wg. mg equals VO of 5 rho wg. So m double dash g, subtraction. 5v minus VO of 5. 25 minus 24v divided by 5. Rho wg, question number, or you can name this star, you can name this double star. The same weight means same submerged volume. Same weight means same submerged volume. So maximum load that can be taken by the second boat. M double dash VO M dash G. 24 VO of 5 rho WG. 4 O 5 rho WG. Simplify 6. No? Answer is answer number 3. Answer is answer number 3. Right. 2 point charges plus Q and minus Q2 are placed as shown in the figure. Resultant electric field intensity could be 0 at a point. So here plus Q, here minus Q. So if I keep a plus 1 coulomb here, positive repulsive, negative positive attracting, here it can never be 0. So any answer with B is not valid. 4 and 5. What can you say here? If I keep a plus 1 coulomb, positive repulsive, negative positive attractive. Negative positive attractive. Right. Now here it can be 0, but what's the condition? This is far away, this is close by, so Q1 should be greater than Q2 actually. If Q2 is larger, then the attractive force will be larger. Okay. So Q1 is larger than Q2 at A. Correct answer is going to be answer number 2. Correct answer is going to be answer number 2. A radioactive source is placed at the bottom of a hole in a lead block. A beam of radiation emanating through the hole is allowed to pass through the magnetic field as shown. 3 separate beams A, B, C could be respectively formed. So here you can see north to south there will be a magnetic field. North to south there will be a magnetic field. Here no deviation takes place means this is neutral. Neutral means no charge. No charge means it can be gamma rays. So B can be gamma. So either this is correct or this is correct. All the others are wrong. Okay. Either this and this are correct. Right. Next one. You can apply left hand rule. Field is in that direction. Current in same direction, let's say. Force is this way, it's going to bend. So this is going to be positively charged. Positively charged means alpha particle. So this is the answer. Fourth one is the answer. Very good. So just by basic application of theory, you can get the answer. Next one. A metal block is hung from a support by string P as shown in the figure. So metal block is hung here. From here on you get the basic relationship. From here you get the basic relationship. Consider the following statements. If Q is taut, the tension in P is greater than in Q. What do you mean by Q is taut? Q has no tension. So here tension in P, weight. So tension in P is equal to the weight, mg. So if Q is thought, tension in P is greater than that of Q. So tension in Q is going to be 0. Statement A. They are saying thought. Thought means what? There is no tension. So which means A is correct. If Q is pulled down slowly with increasing tension, P has a tendency to break before Q. Tension at P is equal to mg plus Tq. So the force acting on Tp is larger, chances are P can break. Correct. If Q is pulled with a jerk, Q has a tendency to break before P. If I pull this with a jerk, look at this. Jerk means I'm applying an impulsive force. So impulsive force means there is less effect on that, more effect on the lower one. So correct. A, B, C all are correct. A, B, C all are correct. We are right there. When we apply an impulsive force on Q, a large force is acting for a very short period of time. A large force is acting for a very short period of time. On the lower charge, on the lower string, on the lower string. This will cause the string to fracture. Right. A decoration consisting of 4 independent rotating sets of small lanterns PQR, all rotations take place around the vertical axis, which is more stable. Rotational stability occurs if all the objects are rotating in the same direction, if the angular momentum is large. So if you look at this, everybody rotating in the same direction occurs only in answer number 4. So angular momentum is large here, so rotational stability will take place. Right. Question number 10. A system of coplanar forces OA, OB, OC, OD, OE, OF are given. OA is equal to 2 times OD. So if I shorten it, actually only so much is left. OE is equal to 2 times OB. Actually only half of it is left. Right. But I am drawing it right now. Resultant is most likely to be. Okay. Start from one vector. Where it ends, start the other vector. Where that ends, start the other vector. Where that ends, start the other vector. Starting point, finishing point K. So resultant is in the OF direction. Okay. Right. Water drains through the opening A1. Cross-sectional areas are given. So if you are a bit smart enough, you can apply Bernoulli, but equation of continuity also. Here there will be a drop in velocity. So A1 B equals A2 V2. V2 is equal to A1 B divided by A2. Now from here I can apply Bernoulli along the same streamline. Here atmospheric pressure just coming out of the atmospheric pressure. Let me take this as the Gp equals 0 line. By applying Bernoulli principle, very good. PATM plus height there is equal to simple h, no? Simple h rho g. Half density of the liquid, velocity is v2 square at the bottom. PATM plus half rho v square. PATM cancel off. Here rho g h, half rho. What is v2 square? A1 v divided by A2 whole thing square. Half rho v square. All the row terms are common, cancel it off. Multiply by 2. From this you get 2gh a1 divided by a2 whole thing square b square. B square, take the other side. 2gh b square common. 1 minus a1 squared over a2 squared. There you go. 1 minus a1 squared over a2 squared. Simplify it slightly further. You will get b is equal to 2gh 1 minus a1 squared over a2 squared whole thing square root. Well, this is given to us by answer number 1. This is given to us by answer number 1. That's the working. So you cannot ignore the level drop. So here equation of continuity. Equation of continuity. Right. Question number 12. A uniform electric field of magnitude 400 volt per meter is acting in the direction shown. So here we can take components actually. So in this direction we have the component 400 plus 60. So 400 plus 60 minus potential gradient. Potential gradient is very respectably, you can easily show this. So negative potential gradient. Negative potential gradient. VB minus VA 0.03. 200 here. So VB minus VA is 6. VB minus VA is minus 6 volt. VB minus VA is minus 6 volt. Easily you can find. Look at this carefully. The internal resistance of the battery shown in the circuit is 0. The value of R0 is adjusted until the voltage across it becomes 5 volt. So interesting, huh? The resistance here is changed until the voltage across it becomes 5 volt. So think carefully, yeah? Supply voltage is 10. Across this 5 means, what can you see? Resistor here and resistor here both are same. So the effective resistance here, is equal to R0. Equal to R0. So equivalent resistance of the part of the network shown by XY. Okay. So here we can say, right, here R0, here R1. This part we don't know, let's say R. So this effective resistance should be equal to R0. When the resistances here and here are equal, only voltage will divide. So I can easily say 1 over R, effective is R0, 1 over R1 plus 1 over R. I'll name it RXY. 1 over RXY is 1 over R0 minus 1 over R1. Simplify the relationship. R1 minus R0, R1 R0. 1 over RXY. Turn upside down, RXY is R1 R0 divided by R1 minus R0. So here you get your answer number 3. Here you get your answer number 3. So very simple. If the voltages are equally dividing, resistance here and effective resistance there both are what? Same. These are not difficult, very basic ideas. You can see 3 identical circular wires, loops, are placed perpendicular to uniform magnetic field of flux density B. The extent of the magnetic fields are different from one another. PQ are shown in the figure. The extent of the magnetic field Q is equal to the area of the loop. So here area of the loop, here smaller, here bigger. Right. When the flux varies, the induced EMF, right? What can you say about the induced EMF? Now here and here, the area linking the magnetic field is the same. So EMF will be the same. So Q and R, the EMF is same. Here the area linking the loop is smaller, so EMF is going to be what? Smaller. So what we can say is, I think we can say very easily, answer number 4, right there. The area linking the loops Q and R are equal. The magnetic fields linking loops Q and R are equal. The magnetic field linkings loop Q and R are equal. But the magnetic field linking the smaller loop, the magnetic field linking loop P is small. Magnetic field linking loop P is small. Therefore, there is a smaller EMF. Therefore, there is a smaller EMF. Right. A rectangular wireframe made from smooth resistive wire is connected to a battery of EMF E with negligible resistance. XY piece is cut from the same wire which can slide along the wireframe. A non-conducting liquid film of surface tension P is formed. The entire structure is placed in a uniform field. XY, all these are XY equal, XB equals XE. The current through AX is I. And the wire XY will tend to move towards the right. Okay. So what will happen? All lengths are equal means here resistances are there. So whatever current comes here might divide. That's one reason. Next is if you look through the loop here. On top there is a film, bottom there is a film. So here there will be a surface tension force. Surface tension into length. Surface tension into length. Surface tension into length. Right. Apply. Field current force. Magnetic force in that direction. Magnetic force in that direction. Surface tension force in the opposite direction. They are telling tends to move to the right. Tends to move to the right when magnetic force is greater than 2 times surface tension force. 2 times surface tension force. Right. Magnetic force is equal to B. What can you say about the current here? Current divider method. Main current 3R times addition 3R or 4R. 3I divided by 4. That's the current. 3I divided by 4 into length L. 2 times surface tension force. Surface tension into length. Right. L cancel off. What can you say about the magnetic field? B is greater than 8T divided by 3I. 8T divided by 3I. B is greater. Correct answer is answer number 1. Correct answer is answer number 1. So here there will be 2 surface tension forces acting. Here there will be a magnetic force. Okay. Question number 60. Question number 60. An ideal gas is taken through thermodynamic cycle as shown in the figure. Process 1 to 2 is isothermal. 1 to 2 is isothermal. During the process, 60 joules of heat enters the system. So here, heat input. joules. Process 2 to 3 takes place constant volume. Output is there. Minus 40 joules. The change in internal energy of the system from 3 to 1. So let's apply delta Q 1 to 2. delta U 1 to 2, delta W 1 to 2. Here it's going to be 60 joules. Internal energy change is going to be 0. Constant temperature. Delta W 1 to 2. Delta W 1 to 2, 60 joules. Then 2 to 3. Delta Q 2 to 3. Delta W 2 to 3. Delta U 2 to 3. Here minus 40. No work done. Delta U 2 to 3 is minus 40. Minus 40 joules. Take 3 to 1. You can basically apply this now. Delta U 1, 2, 3, 1. Delta U 1 to 2. Delta U 2 to 3. Delta U 3 to 1. Cyclic process. Internal energy change is 0. So here you have 0 here. Minus 40. Plus delta U 3 to 1. Delta U 3 to 1 is going to be 40 joules. So our answer is answer number 5. Answer is answer number 5. Write there carefully. In a cyclic process, the internal energy change will be 0. Cyclic process, internal energy change will be 0. Right. Thermometers must possess good sensitivity. Good sensitivity. Like sensitivity as well as good accuracy. In this connection, which of the following is true regarding mercury in glass thermometers? Mercury in glass thermometers. Right. Now, if you look at the sensitivity, there should be a reduced radius. Radius reduces, there is a bigger rise. So, reduced radius means this is correct, this is correct. Increase the volume in the valve, it should not be reduced. So, even these two you can have a look, not that. Okay. What about the accuracy? What about the accuracy? Reduce radius of the capillary. This won't come. Increasing the volume of mercury in the glass bulb. That means technically increasing the volume of the bulb. Okay. Reducing the volume of the glass bulb. So if you reduce the volume of the glass bulb only, quickly it will absorb heat and expansion will take place. So this is correct. I think both are correct. Answer is answer number 3. Answer is answer number 3. Question 18. Two bulbs, 110 volt, 40 watt, 110 volt, 100 watt are connected in series with an electrical supply of 220 volts. So here one bulb is 110 volt, 40 watt. Here you have 110 volt, 100 watt are connected in series with the electrical supply of 220. Electrical supply of 220. Right. Which of the following statement is false? Which of the following statement is false? Right. Look. Current through A is the same as through B. Series same. Potential drop across A is greater than potential drop across B. So here if you take it, same current, power is small, current is same, voltage is small. Power is large, current is same, voltage is large. So if I take A and B, potential drop across A is going to be large. So right, power is equal to VI. Power is 40 volt. Correct? Power 40. Voltage is large. Even though they are saying here power is 40. 40. So you can use this to find the resistance. Power is equal V squared over R. 40 equals 110 squared over R. Next is 100 equal 110 squared over R. So you can look at the resistances here, RA, RB. RA, RB. If you look at it, RA is going to be larger than RB. Larger resistance. Larger resistance means larger voltage. Correct. Current through B is less than the rated current. Obvious. So, if you take 40 volts, the maximum possible current here is going to be lesser than that maximum. So, from this we can get a basic relationship. So, current through B is less than the rated value. Yes. Current through B is less than the rated value. Power dissipation in A is greater. Correct. Larger resistance. There is higher probability of burning the bulb B. Wrong. To supply a voltage of 40 watt here. Maximum possible current here is going to be suitable to this. So this will not burn out. Wrong statement is answer number 5. If you look at this, 40 divided by 110 is the maximum possible current in A. 40 divided by 100 watt is the maximum possible current in B. So B will not burn. B has a larger current. A might burn because A has a smaller current. Figure shows cooling curve of liquid backs on mass M specific heat capacity SL, latent heat of fusion L, heat capacity of the content is negligible. Consider the following statements. Gradient of the curve A dash A is equal to the gradient of the curve at B. This point here. Now, if you look at it carefully, here the gradient, to apply equations, Q dot is equal to K times A, theta minus theta R. Q dot is equal to mass, specific heat capacity, delta theta over delta T. Ka, theta minus theta R. Delta theta over delta T. Ka, MC, theta minus theta R. Here it might be a liquid, here it might be a solid. Specific heat capacity changes. So obviously the gradient will change. Statement A is wrong. So 1 is wrong. 1 is wrong. 2 is wrong. 4 is wrong. The rate of heat released to the surroundings during capital T. So here temperature is constant. Fusion will take place. M over T times L. ML over T. Which is correct. Gradient of the curve at AA dash. Gradient of the curve. So here you can write the basic relationship. So rate of heat loss here. The rate of heat loss here, mass, specific heat capacity of the liquid, delta theta over delta T. At this temperature the heat loss and that temperature heat loss both are same. M will cancel out. Delta theta over delta T, L divided by SL times T. Correct. B and C correct. B and C correct. A tiny sphere with static charge plus Q starts falling through air. Plus Q starts falling through air under gravity. So mg is acting starting from rest. After the sphere has reached terminal velocity, So falling through air means here Ng is there, here resistive force is there, viscous force reaches terminal velocity. After it reaches terminal velocity, so there you go. Now there is an upward electric field, and the electric field is removed. Sorry. After reaching terminal velocity, a vertical upward electric field is applied. Right. Now after reaching terminal velocity, if you apply an upward electric field, there will be an upward electric force. So deceleration will take place. Right. A short time after the sphere changes direction. Sphere changes direction is given. That means it can't be this one. They are in the same direction. VT graph. So changes direction means now the upward electric force is greater than mg. Here starting from west. Now the object is going upwards. After the sphere changes direction, electric field is removed. So the moment it starts going up, again electric field is removed. Then gravity is coming downwards. It will keep on going in the downward direction. So your most probable answers, and again this motion repeats. If that motion is repeating, it will reach the same terminal velocity. So it can't be answer number 3. Right. So your selection is between answer 2 and answer 4. Answer 2 and answer 5. So here deaccelerates, terminal velocity, uniform deacceleration. Then release, accelerates back again, then terminal velocity. Next question is whether this is a straight line or a curve. So deacceleration will take place because when deacceleration takes place, viscous force will also change. When the force is changing, the resultant force will be what? Non-linear. So if you apply mg minus 6 pi eta rv minus fe equal ma. So when velocity keeps on changing, the acceleration will keep on changing. So if you look at the variations here, one is a straight line, one is a curve. So it can't be a straight line, it should be a curve. Correct answer is answer number 2. Right. A student is asked to design an experiment using resonance phenomenon to determine the speed of sound in a sonometer wire being kept under constant tension. The student is supposed to use a graphical method. A set of tuning forks is provided for this purpose. If resonance at the fundamental mode was obtained by the tuning fork, resonance was obtained at the fundamental mode of the tuning fork. They are asking you, write a relationship. So fundamental mode via lambda divided by 2 is equal to L. Lambda is equal to 2L. V is equal to F lambda. F times 2L. So F times 2L is the relationship. Rearrange the above expression in the form of y equal mx, where y is the dependent variable, and this experiment choose y in such a way it's not a reciprocal of the measurement. V is equal to 2FL. Select Y, so it's not a reciprocal. So you can actually change what? Frequency. L is equal to V over 2 times 1 over F. Y is equal to mx. Y is equal to mx4. X independent variable 1 over F. Dependent variable is L. State whether you would start the experiment with the tuning fork having the highest frequency or the lowest frequency. So to have a small vibrating wave, obviously highest frequency. Highest frequency. This will give us a small vibrating wave. This will give us a small vibrating wave. How would you identify the tuning fork with the highest frequency? Tuning fork having the shortest prong length. Shortest prong length has the highest frequency. Shortest prong length has the highest frequency. Why is it easier to observe the resonance state at the fundamental mode of vibration than at overtone? The greatest energy or amplitude of resonance, the greatest energy, or we say the energy release is maximum at the fundamental mode. So greatest amplitude occurs at the fundamental mode. Occurs at the fundamental mode. Occurs at the fundamental mode. Right. Graph is given as shown in the figure. Label the axes. So my x-axis will be 1 over f. So hertz minus 1. Here it's going to be L, I can put it in meters. Right. Labeling is done. Calculate the velocity from this. Right. What are the points which you will consider? So I'll consider this point here. Exactly cutting the grid mark. Also I can take this point here. This point. So 0.0042 0.21. Here we can take 0.0038. 0.39. So gradient of the graph y2 minus y1 divided by x2 minus x1. Simplify the relationship, you can obtain the answer. Gradient of the graph. And 5.88. Gradient is meter per second. Don't forget to put the units. That's the gradient. Then calculate velocity. I'll do it there itself. Velocity is equal to double 2 times 105.88. 16, 17, 11, 2. 211.76 meter per second. 211.76 meters per second. Easily we can find. Okay. The error in the resonance length has two components, the reading error and the instrument used to measure L, and the error due to uncertainty in obtaining the resonance state. How would you experimentally find delta L over 2? Now we keep a paper item. Paper item flies off. We don't know when the paper item, where the paper item flies off. So what do? For the same resonant length, repeat the experiment at least 3 times. And for the same frequency, repeat the experiment at least 3 times. Get the resonant lengths and then find the average. Right? For the same frequency, repeat the experiment at least 3 times. At least 3 times. At least 3 times. And obtain the average resonance length. From this we can find the uncertainty of the resonance state. From this we can find the uncertainty of the resonance state. Right. Okay. Now we have the electric field question. Now there are cathode plates here. Cathode plates. You can see positive charges going there means here it's going to be negatively charged. Negative charges coming here means positively charged. But if you look at it, they have told you these are anodes, anode rods. So these anode rods are positive. Anode rods are positive. And those are cathode plates are negative. Right. Chamber filled with gas. Right. So what are they saying? Detection of photons and other subatomic particles is important in high energy particle physics. A multi-wire proportional chamber is one of the detectors used for such purposes. Application of MWPC can be found in a variety of fields such as nuclear, protein crystallization, particle detection in high energy physics experiments. Right, let's go back to the question. I told you, go to the question, find the answers. Give 2 areas in which MWPC finds application. So I think they have given you the answer here. I'll underline here. Nuclear medicine, protein crystallography, particle track detection in high energy experiments. So this is the answer for Roman number 1. Answer is there. Right. Next question. Which region of the detector has high electric field? Which region has the high electric field? Wait. In this basic configuration, MWPC consists of thin 20 microdiameter parallel and equal space anode wires symmetrically placed between 2 thin metallic cathodes. For proper operation, gap L is normally 3-4 times larger than the wire spacing. Cathodes are earth and anodes are maintained at positive high voltage 3 kilovolts to produce extremely large electric fields. So the anodes here, they already told you that anodes are having very high potential. Very high potential means extremely large electric fields. So here you can see anodes are having high voltage, extremely large electric fields around the wires. So the answer there, Roman 2, around the anodes, having extremely large electric fields. Right. How does a primary electron acquire energy to produce a secondary electron positive ion pair? Wait. When a high energy charged subatomic particle passes through the detector, it collides and ionizes the gas molecules along its path in the chamber, producing certain number of electron positive ion pairs. These called primary ionization. So I'm sure that's what they're asking you. How does primary electron acquire energy to produce secondary electron positive ion? Secondary means next part. Right, keep reading. In the presence certain one electron ion pair, the high energy particles lose about 30 electrons from its kinetic energy. The primary electrons thus created move towards the anode bias and the positive ions to cathode plates due to electric field present. When these primary electrons move close to electron bias, strong electric fields exist around the bias which accelerate them, increasing their kinetic energy. Such energetic electrons move towards the anode bias will collide with argon ions, producing more electron ion pairs close to the bias. This process is called secondary ionization. I think the answer is already there. Huh? So initially ionization takes place. In the collision process there is going to be a loss in energy. Electrons are moving towards the anode bias, the positive ions to the cathode. When the primary electrons are moving close to the anode bias, electric field is very strong. Therefore they will accelerate, increasing their kinetic energy. Such energy collides with argon atoms, producing more electrons with higher energy. This process is called secondary ionization. This process is called secondary ionization. So Roman 3 answer, you can put that. Roman 3 answer, you can put that. Right. Then what? Very simple work, you can see. If the secondary ionization takes place according to the diagram given in figure, how many electron atom collisions are necessary for one primary electron to produce 4 secondary electrons? Including, look at the picture. Electron produces electrons, positive ions, they go towards the cathode. So electrons collide, here producing more electrons. These electrons are accelerated towards the, so they are asking you a very simple question. The question is, if the secondary ionization takes place according to the diagram, how many electron atom collisions are necessary for one primary electron to produce 4 secondary electrons, including the primary, 4 secondary electrons. So 1, 2, 3 collisions. 1, 2, 3 collisions. So 3 collisions are necessary. 3 collisions are necessary. Where in the detector are the majority of positive ions being produced? Where in the detector? So positive ions are produced near where there is positive charge. So near the anodes. Near anodes. Near the anodes. Give 2 reasons as to why positive ion cloud takes a longer time to migrate to a cathode. So they are given you here. See. This will continue until all electrons are collected in the anode bias. Figure B shows how a single primary electron will rise to a large number of secondary electrons through secondary ionization. This number is 10 to the power 3 in pure argon. Its value can be 10 to the power 6 in mixture of gases. Anode bias will finally collect all the electrons in a very short time, leaving a cloud of positive ions around the wire, which slowly migrates towards the cathode. So they are asking you, why does it slowly travel? So one reason may be positive charges have a slow speed. So you can write that positive charges will have a slow speed. Next reason, it's going up, no? Weight of the positive ions is larger. Weight of the positive ions is larger. Right. Next one. Give three properties of the detector that determine the amplitude of the pulse. Three properties that determine the amplitude of the pulse. Electrons collected by anode bias can be observed by current pulse, which can later be converted to voltage pulse. The pulse amplitude produced by NWPC is measured by the energy loss of the particle during passage. In addition to the amplitude, the pulse depends on the detector properties such as the gas use, voltage applied to the anode bias, gap between the cathode plates, wire spacing and wire diameter. There you go. Those are the reasons. Okay. Those are the reasons taking place. Detector properties such as gas use, voltage applied, gap between cathode plates, wire spacing, diameter. Right. Using Gauss theorem, find an expression for the electric field intensity at a distance r from a long straight wire of radius a. Long straight wire of radius a. Carrying a charge per unit length, lambda. So all charges are along a length, infinite wire, Gauss theorem. Don't forget, electric fields will be traveling perpendicular to the surface. Electric fields will be traveling perpendicular to the surface. E times A, sum of charges divided by epsilon. Gaussian surface area. Gaussian surface area 2 pi r h. This height is h. Total sum of charges here, lambda times, along a length only is distributed, lambda times L or lambda times h. Electric field is lambda divided by 2 pi epsilon naught simple r. What would happen to the amplitude of the pulse if the radius of the anode is reduced? Give reasons to your answer. Now look at the thing very carefully. The radius reduces, anode, radius of the anode bias reduce. Radius of the anode bias reduce. Right. So if you look at the radiation, look at this thing. 2 pi epsilon naught simple r, no? 2 pi epsilon naught simple r. Smaller the radius, greater the electric field. So greater electric field means more electrons. More electrons will come in, so amplitude will increase. So you can write greater electric field is produced. Greater electric field is produced. More electrons are collected. More electrons are collected. Therefore, amplitude is large. Therefore, amplitude is large. Right. Figure C shows section of a WBC with two anode wires. Copy this diagram to your sheet and draw the pattern of the electric field inside this section. So what are they saying? Figure where? Figure C. Figure A is there, figure B is there, Figure C is a diagram like this. Figure C is a diagram like this. I think we can go back. Right. Figure C, you have anode here, cathode. They are asking you to draw the field lines. Now here plus, here plus. Positive to negative, you have electric field lines travel. Positive to negative, you have electric field lines travel. Positive to negative, you have electric field lines travel. Always perpendicular to the surface. You have like this. There will be a very strong electric field. So there will be a very strong electric field. Okay. Right. So minimum around 3 fields lines drawn. If a high energy charged particle entering the ejector with kinetic energy of 100 kV passes through the reactor containing 105 electron ion pairs, calculate the energy of the particle when it leaves the detector. So enters with 100 kV, creating 100 primary electron pairs. 100. I think they have given you a percentage value for the loss. In the question itself they are given. They are telling you high energy particles loses about 30 electron volts of its kinetic energy. 30 electron volts of its kinetic energy. When high energy subatomic particles pass the detector, collides and ionizes the gas molecules. It's called polarization. Presents state union of pairs. High energy particle loses about 30 electron volt of its kinetic energy. The primary electrons, the state move towards this. Where? A single primary electron will rise a large number of secondary electrons. This number is 10 to the power 3 for pure argon, 10 to the power 6 for about argon and carbon dioxide. Right. So here you go. Now, how many secondary electrons are created? 1000. If there is just argon. 100 primary electron pairs. Calculate the energy of the particle when it leaves the reactor. Where? Energy of the particle. So 30 electron volts are lost by 1 electron. So 1 electron, 30 kilo electron volts. 30. It's a very simple calculation. 30 electron volts. Yes, 30 electron volts. Right. So 30 electron volts, please convert to kilo electrons. 30 electron volts convert, divide by 1000, kilo electron volts. 0.03 kilo electron volts. How many electrons are generally formed? 100 primary electrons are formed. So 100 electrons are formed means 0.03 times 100, 3 kilo electron volt is the loss. Loss in energy. So 100 kilo electron volt minus 3 kilo electron volt, that will give you remaining is 97 kilo electron volt. So 1 electron, 30 electron volts convert to kilo electron volts. 100 electrons are going in, multiplied by 100. Subtract, that will be the remaining. Is it clear? That will be the remaining. Right. Now we have finished. We have finished week number 9. Okay. Look at this carefully. So 2000 A level, 2001 A level, 2002 A level, 2003, 2004, 2005, 2006, 2001. So if you have done this 1, 2, 3, 4, 5, 6, 7, 8, 8 papers. 8 papers, 60 MCQs, 480 MCQs done. Okay. Then at the rate of 3 essays every paper. We have done 8 papers, 24 essays. 3 structured essays, 8 years of paper, 24 structured essays. So what are the questions we have covered? We have covered the mechanics essay question. Mechanics essay question is covered. Waves questions are covered. Optics questions are covered. Fields questions are covered. Fields questions are covered. This includes gravitational field, magnetic field, electric field questions are covered. Right. Now, slowly we will be adding electricity questions. Electricity questions from next week. Okay. So from next week, electricity questions from the other papers. Now the other papers, I will do it on the 5th week. Electricity questions will be done. From next week onwards, they are also added electricity questions. Then we will be adding electricity questions, properties of matter questions as well. Properties of matter questions as well. So maybe the number of essays now in the paper will increase from one structure, one essay to 2 essays, one structure. Yes, 2 essays, one structure, or 2 structure, 2 essays. So this will be increased from next week. These are also added. So now, by now, you should be able to negotiate these problems as well. So I'll be adding those as well. So we all to do. So next week number 10, we'll be doing what? 2008 A level paper. 2008 A level paper. Okay. Right. So then catch you all next week with another edition of Final Countdown. Please keep working. Believe in yourself, because your result only you can change.